UK, and the data challenges seem quite acute as well. So there seem to be a few questions about that in the chat you might want to have a look at. Okay, thank you. And the other thing might be worth mentioning is I think you're using one of the models that's used for global flood mapping as well, the list flood Fathom model that's been published before. So this is actually an application of a global model at a, albeit a very large catchment, but at a catchment scale. So it's really cool. Okay, so on to our final speaker, Antara. Hopefully you're about ready. If I don't know whether Raphael needs to stop sharing first. Yeah, Raphael, could you stop sharing your screen? And here we go. Perfect.
I could override it. Sorry, Raphael.
Brilliant. Okay, so I'll hand over to you now.
Thanks,
Thank you.
Mark. I'm gonna just minimize this and let's go. Hi, everyone. And today I'm going to be talking about mainly my journey through the PhD of answering one very important question that I guess all of us have often wondered about, which is how can we best leverage the massive amounts of Earth observation data that we are producing for improved flood inundation forecasts? And the main question that I was chasing after was, what if most satellite-based flood observations could significantly improve forecasts? So what if my before forecast could look like this and have a lot of false alarms and problems, and my after forecast, after integrating maybe just one remote satellite observation, could look somewhat like this, where I've reduced most of the false alarms? Well, how will it work? One of the ways to do it is to try and make improvements at every step of the process. So we try to first improve the flood extents that we can derive from our satellites. We then try to improve the integration algorithm of these flood extents with our models that we were hearing about so far. And finally, what I wanted to look at was what are the best ways, or which are the best images that we could acquire to facilitate this process as best as possible. So in the interest of brevity, I will be omitting the calibration part and focusing on this part today. Let's dive in. And the first part of this project was to improve the radar-based flood mapping. And the main challenges in front of us were major histogram dependence and over-reliance on deterministic outcomes. So let's first talk about the first problem here. So a typical flooded image histogram is assumed to look somewhat like this, where we have a nice water pixel distribution and a nice land pixel distribution, a nice bimodal histogram, and then we can divide it using a binary threshold and get a flood map. In reality, however, there's often significant amounts of overlap, which prohibits this sort of threshold-based mapping, or at least introduces significant amounts of uncertainty. What we can do then is try and use a probabilistic distribution. The most commonly used one is the Gaussian mixture model, of course, as these curves can be assumed to be Gaussian, and we can then parameterize these distributions in a data-driven manner. And this still, it kind of helps us with the deterministic threshold problem, but it does not help us with the histogram dependence. So what we proposed to do for that was image texture optimization. And the reason for doing this is essentially that in a histogram, which is evenly divided between flood and non-flood pixels, there could still be a whole variety of different patterns that could exist in the actual flood extent. And we essentially could miss them if we only rely on the intensity values. So trying to incorporate texture led to a different set of problems, which was how to objectively select them, or how to retain only the information that we need, because we cannot indefinitely increase processing time. So we tried to come up with an objective methodology to achieve this. We first calculated the sensible variance within each of the classes, so the flood and non-flood classes, and based on the data resolution, which in our case was Cosmos SkyMet data at 3 meters. So we got a lag distance of 3 pixels. Then we removed the effect of directionality from texture. So as you could imagine that if we are checking, if we want to create a texture map of, say, this central square, depending on which angle I'm looking at, the pattern that I would discover would be different. So in order to remove that effect, we averaged out the textures in all directions. And then, as I said, we cannot indefinitely increase processing time. So we condensed all our information into the minimum possible number of bands using a dimensionality reduction technique. And we had our optimized texture features. I'm showing here the results of a fuzzy comparison between SAR-based flood maps and aerial photo-based probabilistic flood maps. And the comparisons on the screen are for a neuro-fuzzy classifier implemented to the SAR intensity image alone, a SAR image enhanced with the standard textures used in literature. And the final panel shows the classification enhanced using our optimized textures. The blue colors are a perfect match, the red colors are a perfect mismatch. And it quickly becomes evident that as we go from the left panel to the right panel, we are significantly able to reduce uncertainty. And one more interesting finding is that when we add some texture, so any texture, we do not make as much improvements as we would with optimized texture. Now, looking at a lump statistic, which can quantify what we see here, we look at a reliability diagram and we try to calculate the weighted RMSC from this reliability diagram. So what we are looking at is the plot between the observed proportion of wet pixels in the validation data and the fuzzy membership value observed in the SAR map. And the 1-1 line indicates perfect agreement. And the triangles, which are the SAR plus optimized texture, we can see are already the closest to the 1-1 line. And in terms of the weighted RMSE statistic, we make about a 54% improvement. But what's even more vital to note is that the addition of some texture only makes very negligible improvements, while when we optimize our texture information, we are able to reduce our errors significantly. So we now had a working flood extent mapping algorithm. It was working as well as we could hope. So we needed a new method to combine these satellite-based flood maps with our models. And here, the main challenge was having the sensitivity of our metric that we use to compare our models to the observation. So essentially how probabilistic forecasts work, and please forgive me, those of you who are already familiar with it, we have an ensemble of models which we expect or hope that will capture the uncertainty in any one of them, in any one of those models. And at any time during the flood event, we hope that at least one of them or a combination of these models is true. And the problem is when we want to choose that metric for flood extents, the difference between models is usually very limited to be able to capture it with these metrics, since the common area often or mostly outweighs the area that is different between different models. And the solution we propose to this is to embed a likelihood, which I'm going to come to in a minute, within a particle filter algorithm. Particle filters do exactly this. So we have our ensemble of models and we have no information about which one is right. So we assume that all of them are equally likely to be true. And as and when we get observations, we iteratively update our model ensemble probabilities or the likelihood of any of them being true, such that we can eventually estimate the true state PDF. Sorry, the final ranking of models which give us the best forecast. So here we propose to use mutual information as the likelihood which allows this model ranking. And mutual information essentially starts with the assumption that the model ensemble and the observation are completely independent. And if they are statistically independent, the joint distribution of these two should be equal to, in theory, to the product of the marginals. Getting a little bit technical here, but I'm going to try to walk us through it without getting too boring. So basically what we want to do is we want to get the distance between this joint distribution and the product of the marginals, which would then quantify the shared information between both of these. And this blue shaded distance that you can see from these two example probabilistic distributions are essentially what we are after. And as I said, sensitivity was one of the key issues that we were trying to address. So we introduced a rescaling factor to sort of zoom into this metric and be able to see the differences between our models. This worked fairly well in our test catchment, which was Clarence in New South Wales, Australia. And my test event was the 2011 flood event, for which you can see the hydrograph on screen. We had 2 Cosmos SkyMet images and the open loop ensemble, which is the ensemble without any assimilation or integration with remote sensing data, is shown here. And the mean is also shown here, along with the truth, which was used as the base scenario, or the observed flows, which were used as the base scenario to generate this ensemble. And we found that our assimilation algorithm works fairly well, actually. Within the channel here, we are looking at this point, Grafton, which is one of the key areas to get right, since there are a lot of settlements here, which are at risk from the flooding. And the green line shows the true stage, while the black line shows the open loop, again, without any assimilation. And the dashed magenta line shows the assimilated vector. Image positions are shown in dashed black lines. And we can see that following both the assimilation time steps, we actually drag our open loop vector, the state vector, quite close to our truth. So the water levels actually follow the truth very closely after the assimilation for a long time after the assimilation. We also saw that not just in the channel, but even in the floodplain, in terms of flood extent, we were able to improve the critical success index, which measures the ratio of the hits to the hits, misses, and false alarms, by about more than 10% for at least 3 days. So with these encouraging results, we now wanted to find the best observations that could result in the maximum improvements for our flood forecasts. And the main reason for trying to evaluate this was that for large catchments, often we can observe only small parts of the catchment. And since we can task satellite acquisition, it makes sense to then evaluate which part of the catchment we should ideally be looking at. And the potential solution to this was visualized as sort of designing targeted observation strategies based on river reach characteristics. And the way we went about it in our catchment was using a combination of the channel geometry and the floodplain morphology. And based on this, we identified 3 distinct subreaches in our catchment. The first one with limited backwater effects and actually no backwater effects and a narrow and steep valley, mostly linear flows. The second one with strong meandering, strongly dynamic flows, but a flat, gentle valley and very limited backwater effects. And finally, we had subreach 3, which was quite hydrodynamic, but also affected by dominant backwater effects from the very high tides at Yamba. So trying to visualize our thought here. So how does the ensemble look in terms of extent? So this is the image we were looking at in the couple of slides ago. And at this example observation time, I've sort of extracted the flood extents for this high discharge particle and this low discharge particle. And we can see here that they significantly differ, A. And B, when we compare them to the flood probability map, they should ideally have very different weights. And C, that when we look at the extent variability within the extents of all the particles, here particles means the model ensembles that we were previously referring to, we see that there's mainly the variation is limited to this part, at least at this time step. So with this sort of visual in mind, let's approach our results. Here we will be looking at the Brier Skill Scores, which measure the improvement in the quadratic errors in the open loop forecast against the assimilated forecast. And this is just a snapshot of the catchment to remind us all where the gauges are. And in each of the columns, the gauges are, only those gauges are listed which are within that particular subreach. And what we're looking at here is essentially the Brier Skill Score plots with respect to the satellite acquisition time. So each point represents the improvement in the assimilated forecast versus the open loop forecast, and can be interpreted as percentages. So you could say this point is about 80% better than the open loop. And what we mainly want to be looking at is which image or which of these single images leads to the maximum improvements in our forecast. And a Brier Skill Score of 1 means 100% improvement. So the first really encouraging thing is that a lot of images that we use across the hydrograph produce quite notable improvements. But let's look at also a bit of the discouraging news. So we do degrade our forecasts in places. So let's try to diagnose when and where that happens. And the first thing that becomes quite obvious is that when we assimilate downstream, so when we are assimilating images only in subreach 3, that is the blue curve, we find that the impact is not so great in subreaches 2 and especially subreach 1. And it looks like we're unable to select the models which perform well based on subreach 3, we are unable to select models which perform well in subreach 1 based on subreach 3, which is expected, of course, since we cannot propagate our improvements upstream as such. But when we look at subreach 1, also the red curve here, we can see that even when we propagate our improvements downstream, the improvements from subreach 1 seem quite inconsistent. This is maybe relevant to what we saw in the previous slide, where the variability in extents actually changes across each of these subreaches as we traverse the flood event. And the most stable we realized was assimilating in subreach 2, which was sort of still dynamic. So a bit of extent variability with flat floodplains, but not as much dominant backwater effects, which would then make the dominant source of error something else. Whereas here we were looking at mainly inflow errors. And we found that assimilating in subreach 2 does not actually degrade the forecast downstream at all. And we actually get fairly good improvements, or at least greater than 30% improvements in all the cases that we expected to work. So the key thing to note from this experiment was that based on where we are in the event and how the catchment is, it might be possible to design a good observation strategy, which would lead to then the maximum possible improvement from our assimilation. The way forward then is to develop a better observation localization strategy in space and in time, which would help us then to scale to larger areas. We want to test our approach for different catchments and more real cases to evaluate all sorts of possible cases where maybe it implodes. And finally, our goal is to scale for global implementation and try and integrate this approach with GLOFAS. And thank you so much for your time and for having me here. I'm happy to take any questions or feedback now.